The only objects in the universe that can trap light by sheer gravitational force are black holes. Scientists believe they form when a massive star's corpse collapses in on itself, becoming so dense that it warps the fabric of space and time. And any matter that crosses their event horizons, also known as the point of no return, is helpless as it spirals into an unknown fate. Despite decades of investigation, these monstrous cosmological phenomena remain a mystery. They continue to astound scientists who study them. Here are some of them. Number 1. Black holes do not suck. Some people think of black holes as cosmic vacuums sucking in the space around them. But in reality, black holes are just like any other object in space, albeit with a very strong gravitational field. If you replace the sun with a black hole of equal mass, Earth would not be sucked in. Instead, it would continue to orbit the black hole as it does now. Black holes appear to be sucking in matter from all directions, but this is a common misconception. Companion stars shed some of their mass in the form of stellar wind, which falls into the grasp of its hungry neighbor, a black hole. Number 2. Einstein didn't discover black holes. Although Einstein's theory of relativity predicts the formation of black holes, he did not discover their existence. Instead, Carl Schwarzschild was the first to demonstrate the existence of black holes using Einstein's revolutionary equations. He accomplished this in 1915, the same year Einstein published his theory of general relativity. The Schwarzschild radius is a measurement of how small you'd have to compress any object to create a black hole as a result of Schwarzschild's work. Long before this, British polymath John Michell predicted the existence of dark stars with gravitational pulls so strong that not even light could escape. Black holes didn't get their universal name until 1967. Number 3. Black holes will spaghettify you. Black holes have the amazing ability to stretch you into a long spaghetti-like strand. Appropriately, this phenomenon is called spaghettification. Check it out. It works because of how gravity behaves over long distances. Your feet are currently closer to the center of the Earth, and thus more strongly attracted than your head. That difference in the attraction will start working against you in extreme gravity, such as near a black hole. As your feet are stretched by gravity's pull, they will become increasingly attracted as they move closer to the black hole's center. They move faster as they get closer. However, because the top half of your body is farther away, it is not moving as quickly toward the center. As a result, spaghettification occurred. Number 4. Black holes could spawn new universes. It may seem strange that black holes could create new universes, especially since we don't know if other universes exist. But the theory behind this is still being researched today. A very simplified version of how this works is that, when you look at the numbers, our universe today has some extremely convenient conditions that came together to create life. We wouldn't be here if you changed these conditions even a little bit. The singularity at the center of black holes violates our standard laws of physics and, in theory, has the potential to change these conditions and spawn a new, slightly altered universe. Number 5. Black holes pull the space around them. Consider the space to be a stretched rubber sheet with intersecting grid lines. When you place something on the sheet, it sinks slightly. The larger the object on the sheet, the deeper it sinks. The sinking effect distorts the grid lines, causing them to become curved rather than straight. The deeper you drill into space, the more space distorts and curves. And black holes create the deepest wells. Nothing, not even light, has enough energy to climb back out of a black hole, which creates such a deep well in space. Number 6. Black holes are the ultimate energy factories. Black holes can generate more energy than our sun. The mechanism is based on the disk of matter that orbits a black hole. The material closest to the event horizon's fringe on the inner edge of the disk will orbit much faster than the material at the very outer edge of the disk. This is because the gravitational pull is stronger near the event horizon. Because the material is orbiting and moving so quickly, it heats up to billions of degrees Fahrenheit, which has the capability of converting mass from the material into energy in a form known as blackbody radiation. Nuclear fusion, on the other hand, converts about 0.7% of mass into energy. The environment surrounding a black hole converts 10% of its mass into energy. That's a significant difference. Scientists have even proposed that this type of energy could be used to power future black hole starships. Number 7. There is a supermassive black hole at the center of our galaxy. Scientists believe a supermassive black hole exists at the center of nearly every galaxy, including our own. These black holes act as anchors, holding galaxies together in space. Sagittarius A, the black hole at the center of the Milky Way, is more than 4 million times more massive than our Sun. Although the black hole, which is nearly 30,000 light-years away, is currently dormant, scientists believe it erupted in an explosion that may have been visible from Earth 2 million years ago. Number 8. Black holes slow down time. Consider the following twin experiment, which is frequently used to explain how time and space interact in Einstein's theory of general relativity. One twin remains on Earth, while the other travels at the speed of light into space, turns around, and returns home. Because the faster you move, the slower time passes for you. The twin who traveled through space is significantly younger. When you reach the event horizon, you are moving at such high speeds due to the black hole's strong gravitational force that time slows down. Number 9. Black holes evaporate over time. Stephen Hawking predicted this unexpected discovery in 1974. Hawking radiation is named after the famous physicist Stephen Hawking. Hawking radiation disperses the mass of a black hole into space and over time and will continue to do so until there is nothing left, effectively killing the black hole. As a result, Hawking radiation is also referred to as black hole evaporation. Number 10. Anything can become a black hole, in theory. The only difference between a black hole and our sun is that a black hole's center is made of extremely dense material, giving the black hole a strong gravitational field. Because of the gravitational field's ability to trap everything, including light, black holes cannot be seen. In theory, you could turn anything into a black hole. If you shrunk our sun to 3.7 miles across, for example, you would have compressed all of our sun's mass into an incredibly small space, making it extremely dense and also creating a black hole. The same theory could be applied to Earth or your own body. However, we only know of one way for a black hole to form: the gravitational collapse of an extremely massive star 20 to 30 times more massive than our sun. Number 11. Black holes can merge and get bigger. Galaxies tend to merge and become more visible as a result. When this happens, however, black holes do the same. Many people believe that such collisions produce supermassive black holes. The Andromeda Galaxy is currently on a collision course with our own Milky Way galaxy. The supermassive black holes at the centers of the two galaxies will merge into an even larger black hole when they merge in about 4.5 billion years.